Hey, thanks so much for hanging around this whole time. I'm very sorry I was late. It's funny, I don't live in the Bay Area. So it's the one time I come down to the Bay Area, what happens is I get on a Caltrain, and then the next thing you know, with big accident. So, I don't know, in case you're curious, actually, I don't think our train hit someone. They thought we hit someone. And then they said that we didn't hit anyone. But then the train behind us hit someone. And when you hit someone, what happens is that when the crew has to be dismissed. So at Palo Alto Station, they dismissed the crew. They said it could be like 60 to 90 minutes. And so anyway, so thank you for your patience. By the way, is anyone heading back down to the South Bay after this? Oh, sweet, that's awesome. I wouldn't mind a ride. So if one of you guys are interested in giving me a ride back to the South Bay, I'm all yours, and you can pick my brain.
We go to Military and then we drive down. Is it okay with you?
That's okay. That's okay with me. Yeah. So anyway, thanks for hanging around. My name hopefully you guys are not in a hurry or anything. I can hurry through the slides, but if you're not in a hurry, I can go through all my slides. So my name is, once again, my name is Evan Chan. I'm an engineer at TupleJump. I actually just joined 2 months ago. I'm quite excited. I have a colleague of mine here, Helena, and it's pretty awesome because we're distributed. So we see each other at meetups, conferences, and that kind of stuff. And just a little bit about myself. This is my Twitter handle if you want to follow me, that kind of thing. I've been doing big data stuff for a number of years. Working with Cassandra since very early days, since the before 1.0, actually 0.6, and working with Spark since about 0.8 and contributing to it and stuff. I remember when I first started working with Spark, it was a really neat little project, but there was almost nobody using it. But it's been amazing to see. Like now, it's like everyone. You can't go to a conference without talking about Spark, pretty much, right? And I also maintain the Spark Job Server project, which, if you're curious, I can talk to you about it later. It is a REST server for running your Spark jobs. A little bit about TupleJump. We are a big data technology leader, and we provide solutions and development partnerships. I guess that's a nice way of saying that we provide consulting and help architects and do projects. We have a couple of pretty interesting projects, including an open source HDFS on Cassandra implementation, as well as a Lucene indexer. And PhiloDB is the subject of today's talk. And we have an alternative Spark Cassandra integration layer. This is just a mandatory slide for me to show that we offer big data development expertise, all kinds of different stuff. We've done a lot of interesting projects. Including, traditional help companies ramp up their big data stack, as well as some other really interesting projects, including porting open source projects to Spark and things like that. So just to start off the day, we got to have a Dilbert cartoon, right? So I'll give you a minute to look over this, since it's about analytics. So anyway. So I saw this quote that big data is yesterday and fast data is now. How many people have heard of the term fast data? Like I think TypeSafe has talked about it. The idea is that fast data, so big data everyone knows, you have more data than you can handle in one node. The idea of fast data is that now we have data that's coming in that's real time, coming in from more and more sources. So you could have sensors, right? There's a lot of talk about smart cities. So that cities want buses to be constantly transmitting information. And then they want to use that to maybe improve how they do parking, or give people tickets in real time, or this kind of thing. More revenue for them. And of course, you have the likes of Uber and Nest and all kinds of devices, right, that are constantly sending data. And so every company is getting a deluge of data from all kinds of sources. and you want to react and take advantage of it right away. So that's what fast data means. It's like data that's coming in fast, reacting fast to data. That's what it means by fast data, right? Oh, I guess I had what it means slide. It's not enough to just react though to data as it comes in, right? Like, so this is, if you want dashboards, you want to find out how many people are using your service right away. That's really good. But usually you need to combine it with some existing data as well, right? You need to, so you need both. You need fast data and you need big data.
So, is it okay to ask questions? Or?
Yeah, go ahead, yeah.
So usually what I notice is put ahead and then you ask the end question, what are you going to do with this fast data?
Yeah.
Our team will look at it in 2 days.
Yeah.
At that point, it's useless what that time takes. But if your business process is set up in a manner that you can take actions on that fast data and be agile, then it makes sense. But a lot of times I notice we ingest, it sits over there, someone else will take a look at it. So
I see. I don't know if I have anything to add about that, but I think you're right that, you want to automate the whole cycle. Yeah. Like you come in and you can derive insights, and then someone has to, so it does have to make business sense, right? Like someone has to actually want it.
Yeah. If there's a person
I do agree with that.
I don't care how fast it is.
Sure. So let's talk architecture a little bit. How many folks have heard of Lambda architecture? Seems like that's become a very popular buzzword. So this slide is from MapR. So in case you're not familiar with Lambda architecture, what Lambda architecture says is, I want to deal with data that's coming in and the big data. So what I'm going to do is I'm going to set up 2 pipelines. I'm going to have a speed layer that takes data and processes it in real time using a system such as Storm, or now they would be like Spark Streaming. And so I'm going to do incremental calculation and then kind of write it into some kind of, usually a key value store. In this case, it's HBase, but I'll be talking about Cassandra a little bit. And that's good for the real-time stuff, but we don't really trust our speed layer, so we're going to have a batch layer that's going to really capture the same data, and it's going to compute it and do the exact calculation, right? So this is the idea of Lambda. And at some point, so now I have data that's computed with the speed layer and a batch layer, and I need to merge them, right? Because now I have kind of 2 answers. I have like this answer for the short-term stuff, and I have answers that have been computed over historical stuff. Now I need to merge it. So that's the idea of the Lambda architecture. And you can see that this involves a lot of different technologies. Like there's like the real-time system and the Hadoop system, and you gotta like have a key value store and you gotta combine it. So what happens when you start implementing these things is that, you'll find that this is actually pretty hard to implement. You got a lot of moving pieces. You have to actually deploy and productionize all those things. You have to monitor all those things. So this is a lot of stuff to implement. And a lot of times you might be running similar code in 2 places, because if you're doing aggregations, chances are you'll probably be doing aggregations in both your batch layer and your speed layer. And you have to reconcile queries against 2 different places. So this is a lot of work, right? And so we have to ask ourselves, is it possible to do better? So I'd like to start a new hashtag called NoLambda. And the idea of NoLambda is we want to build more of a unified system. We don't want to build 2 systems, a speed layer and a batch layer, because this is just too much work. Right, so we want to explore what does it look like to have a single layer that is fault tolerant, that is precise, but can give us real-time processing as well as big data analytics, that we combine fast data and big data. Right, so I'd like to talk a little bit about the SMAC stack. This is what SMAC stands for is Scala and Spark, a Mesos, Akka, a Cassandra, and Kafka. I won't talk about all those things, but I'll mention a few. Spark Streaming is, how many folks have not heard of Spark Streaming? Awesome. So this is an overview, right? That data comes in. The idea of Spark streaming is that you compute mini batches, which are from half a second on up. For most people, that's adequate time scale. And it runs the same computations that Spark, the batch layer, computes. It's just running them in much smaller intervals, right? So that gives us our stream processing layer. We have Cassandra, which is a key value database. I think, how many folks have not heard of Cassandra here? Right. So yeah, I don't think I need to go into this too much, but the idea is you need a data store to write your stream processed answers to. It's fairly easy to get up and running with doing analysis on top of data in Cassandra. We just read it out of a Cassandra table. You can, if you want to do SQL, you can register it in Spark as a data frame. Then in data frame, you have a couple options to do it. You have a DSL as well as you can run SQL queries. Right. So this is also.
Question: what happens when you do a cache table over there?
Oh yeah. Right. So cache table. So data frames has a table. So everyone probably knows you can cache RDDs in Spark, and that keeps it in memory. But Spark SQL and data frames actually has a different table caching mechanism. This is different from RDD caching. It's a lot more efficient. It actually turns the data into columns and caches it in a very efficient way. So it takes up less space, and it's also much faster for reading. So this is something that you could take advantage of to make your queries very fast. So we can say that Spark provides the missing analytics piece to Cassandra. Cassandra is typically used for key value lookups, but with Spark, you can run a lot of deep analysis over it. But what are we missing? So far with the SMAC stack, we have Spark streaming that can do stream processing. We have Cassandra that can do storage. We have an analysis engine on top. So let's say you're writing events now into Spark. Then I can analyze it. So what are we missing?
Can I ask you another question?
Sure.
So if you're not able to ingest the data, right, and you have a problem where the pressure is building, how do you've got to pull the data. You need to keep the stuff that is doing the real-time streaming. You cannot ask that to slow down. So you need some buffering in between the part from the streaming to the point you actually access it.
Thank you. So there's Kafka, the queuing system, which provides buffering. Yeah. Well, there's many reasons why you would want to use Kafka, yes. But that's one reason is that you can buffer. And
so the cache table actually integrates with that also? Or?
No. Cache table is only in Spark. Yeah.
Okay.
Yeah. So what I would argue is that what we're missing is reasonably fast analytics on top of Cassandra. So Cassandra is very good at storing a lot of small values concurrently and reading them out, but it's really slow when you want to read a lot of data out. That's one thing that HDFS is very good at, is reading a lot of data, but it's kind of the opposite, right? So basically, reading a lot of data out of Cassandra is very slow. You'll find that, like, compared to the same data in say, Parquet, it's about, say, 100 to 300x slower. And so that becomes a bottleneck when you're trying to do anything that requires speed. Like today, people use Spark and Cassandra for things like ETL and loading data in, loading data out, but they're not really using it for analytics. And I would say that's probably one of the key bottlenecks. What about Parquet? So Parquet is, so today a lot of people are writing, if they do analytics, they would write, if they're doing key value lookups, they will write in Cassandra. For doing analytics, they write into Parquet. And Parquet is really good at that for static data. The problem is that being a file format, it is read optimized, but it kind of really sucks if you're trying to write data into it, especially for streaming, and especially if you want to do time series or IoT or anything like that. It's one reason is that it doesn't support idempotent write. So it's not like a database where I can write into a primary key. And if I write to a primary key again, like Cassandra, you know that it will write to the same place. So in Parquet, you end up, like, let's say you have a failure somewhere in your pipeline, you don't know where. You end up having to write data again. And so typically what people do is they will run jobs to deduplicate your data. But this adds a lot of overhead. Exporting data or setting up a parallel pipeline from your streaming source into a Parquet, is also another step. And what I would argue is that what people really want is a database-like abstraction, and not so much a file format. Right. Like what we really want is, let's say that we could have one pipeline for fast and big data. We talked about the SMAC stack earlier. So this is Spark Streaming is the S, and we have the K here. And I don't show Mesos or Akka, but it's somewhere in there. There's Cassandra. Like, what if we could make the stack work for fast data ingestion as well as for big data for ad hoc analytics? And that's what I wanted to talk to you about today. There's this quote that I like. It says, all hard work leads to profit, but mere talk leads to poverty. So for a long time, we talked about architectures, that there's got to be a better way. So now it's time to do something about it. And so that's why we decided to write an open source PhiloDB. So this is the URL here. It is on our repo on TupleJump. The tagline is that this is a distributed versioned Columnar analytics database that is built for streaming. And so the rest of tonight, we're going to go into different parts of that and how that solves this problem. So first, what is it? It is distributed. It is currently built on Cassandra as the storage engine, which is very rock solid, and it's been proven with kind of like the peer-to-peer design that has no single point of failure and all this stuff. Don't need to go into that too much. It is versioned. I will explain more what this means later. But you can think of it as it's kind of like Git, like you can control the versioning of your data yourself. This is a pretty new concept. You can add a few rows as a new version, and you can roll back changes. It's very, very neat. But I'll go into this a bit more later. It is columnar. Now, there's a lot of, Cassandra itself is sometimes talked about as a columnar database. But what I mean by columnar here is that it is like Parquet, where I store things grouped by the column of my data so that I can pull out for analytics. Typically, you ask questions about a subset of your data. Like I might want the highest price average, or the top 10 items in this or that, right? So typically for those kind of reports, you're only pulling out a subset of columns in your table. So why have to scan every column, right? Why not pull out just the data that you need?
So can you go back to the slide, the versioning when you do it? So when you version, are you talking about adding new columns and things like that?
I'll explain that in a bit, yeah.
So about Columnar. So when you select, can you go to
This one.
Storage layout. So
Yes.
you select use Cassandra.
Yes.
Cassandra doesn't say in this format. So
You're absolutely right. Cassandra doesn't by default. I'll show you what we do a bit later.
do you use different compaction strategy and different pages?
We basically store data in a binary blob format, so that it's a lot more efficient. But I'll actually show you what the table layout looks like. And you can do Spark SQL queries on it. So you can run all the standard SQL that you're used to, including joins and things like that. You can create a temporary table in the Hive Spark thing. Basically, PhiloDB lets you use the Spark Data Frames API that you're used to. And so you can easily pull data from any source that Spark supports. You can write into a new table easily using Spark Data Frames, and you can pull data out and run SQL queries. And another advantage of using Spark this way, instead of like some databases use JSON or their own query language, is that you can easily connect it to industry standard tools like Tableau or any other JDBC analysis engine. You can plug into it and run your reports.
Does it leverage Cassandra? Spark connector or it's yours?
No, it doesn't leverage it because the way that we store the data is very different. So we need to pull data out and reassemble it in a different way. It's not standard Cassandra records, which maybe I should just skip to. Well, if you wait a little bit, I'll show you the slide that shows our table layout, and you'll understand.
Just ask excellent question. I have a slide.
Yeah, we have a slide. Yep. What's in the name? Well, I like food. So because it's a version database, it's basically based on PhiloDB, on layers of data. And you can also think of columns as layers of data. And I like desserts. So anyway, that's where the name comes from. And finally, it's built on the type-safe reactive platform. It's built on Scala, Spark, and Akka actors. So it's fairly easy to contribute to. So why? Why do we care about this? And why should I use it? I would say a big reason is performance. It offers a huge performance boost over native Cassandra for analytics queries, pretty much on par with Parquet. So you get Parquet performance, but you get the flexibility of Cassandra, meaning that you get primary key-based ingestion. You can write data to the same key and know that I'm getting exactly once ingestion. And I'm getting the benefit of being able to write data in and update it all the time, which is fairly unique and hard to do. Basically, combining streaming and columnar this is pretty bleeding edge. It is designed for streaming, as I had mentioned, that writes are idempotent. And it's fairly easy to ingest data from Spark Streaming or Kafka. Today you can use the Kafka connector in Spark Streaming, but we're thinking of adding support for Kafka ingestion directly. And just depends on user feedback. So, and it keeps the data sorted as being ingested. So basically, you decide how you want to sort your data, and it will keep your data relatively sorted. So this is what the fills in this missing part in the diagram. Basically, you can think of it as, for example, Spark Streaming writes. It's like an extra layer on top of Cassandra. So you can write data this way. And the idea is you can still, for certain things, you'll still want to use Cassandra, such as I have 100 millisecond key values that I want to write to Cassandra. So you can still use Cassandra for that. But now you can actually write your raw events or semi-aggregated events to PhiloDB, and now you get very rich analytics very fast, just like you would with Parquet, except you don't need to set up an entire Hadoop stack. You can actually use the same stack for everything,
So
which is pretty cool.
And this is the data warehouse, is that right?
Sorry?
The top part is OLTP and the lower is data warehouse.
Right, so this is OLTP and this is OLAP. Yeah, but it's the same stack, which is pretty cool. So for example, let's take an event time series example. What we do is that we model our data using two concepts. One is the partition key, which you're familiar with if you use Cassandra already, which distributes your data around a cluster. And the second concept is what we call a sort key, or this is equivalent to Cassandra's clustering key. Basically, within all your data that belongs to one partition key fits on one node. So the sort key is how the data within a single partition is sorted. So for a time series, what you might do is, for example, the partition key might be your events or your machine entity, right? That might be like 1 device or 10 devices or something like that. And your sort key might be timestamp. And so you would have your data laid out this way, where the data for your device is kind of laid out over time. It's pretty standard time series stuff. The only difference is that instead of a normal Cassandra layout, PhiloDB will keep your data written in a very efficient columnar format that allows you to read it out very fast. Right? There's another option, which is experimental, but you can also keep all your stuff in memory. So let's say that I have Spark Streaming. This data is coming in successive RDDs. I can actually have this data ingested into an in-memory column store. And you might ask, how does this compare to like RDDs, right? So RDDs are immutable, meaning the data in there is static, right? There's two big differences, which is one is that with an in-memory FiloDB, you can ingest new data in there. So it's not like RDDs. So you can keep ingesting new data. Of course, at some point, you need to get rid of old data. But this can keep ingesting new data and keep it sorted. And then the other thing is that it can filter data in multiple ways. So RDDs are basically meant for full table scans. So you need to go over all your data. But this would allow you to filter in multiple ways, such as you can filter along your partition key or along timestamp or things like that. Here's an example of connecting Spark streaming to PhiloDB. We have a stream of data, a rating stream, which is pulling from Kafka using the direct stream connector. And we're going to, so what this, and then what we do is we do a for each RDD, which basically as each chunk of data comes in, Spark streaming is going to give it to you as an RDD. And we're going to take that RDD, which in this case is a bunch of strings, and we're going to extract out stuff from the strings and basically convert it into a data frame. We're going to convert it to 3 columns, a user ID, well, a source and destination user ID and a rating. This data set is actually based on kind of, you can think of it as kind of like a dating website or something, right? Where you have like one user likes another and gives him or her a rating or something. And this is the key part where I take my data frame and I do a write. And this one is pretty much identical to how you would write it to Cassandra or to any other data source, except here I'm using a different format called philodb.spark, and I decide what data set to write it to, which a data set is a table. So this is pretty much a one-line change from how you write to Cassandra to writing into PhiloDB. It's pretty much identical semantics. So I said that would be a slide on versioning. So I think versioning, this is why it matters. Databases pretty much have been the same since the 1970s. You can think of databases as globally mutable state, right? So in your Java programs, you have like mutable state that you share through Java util concurrent. A database is pretty much a distributed version of that, right? And the idea hasn't really changed since the 70s. And now, this is sort of a chance to rethink database a little bit and think, well, instead of just mutating state, I can have explicit versions. So if I have new data, I can write it into a new version, and I can isolate people from the new changes. So let's say that I have some new change. It doesn't propagate all the way. I can keep people reading on an existing version of data and control exactly when that new version gets exposed. So I think versioning, or at least explicit versioning, gives us a way to think about databases a bit differently and enable a lot of streaming applications. Question?
So in breaking Cassandra, if you update a record multiple times, to get the latest record, you would have to read over all the old records to be able to get the last one. Does the architectures do the same thing?
So what you said is like in Cassandra, if you write old records and you overwrite them, you have to read over the. Actually, that's not true. It depends, right? So if you write a new record on top of the old record at the same primary key, you will sooner or later get the new record only. But you might see the old one if wherever you're reading from has not caught up, which is the beauty of or dangers of eventual consistency, right? You're probably thinking of HBase. HBase will let you read multiple versions. Or you can just version stuff yourself. So you can have a primary key where you add in a timestamp, and then so you can explicitly control versioning yourself. You can do it that way. But Cassandra actually usually only returns you the latest data. Yeah.
So are you using versioning as views in some way? Or?
You can think of them as views. There's different ways to think of it. You can think of it as views. Like basically, I can put changes into a version. I can implement MVCC that way if I really want. Or I can think of it as let's say time series. I can think of versions as units of time. like I can have each day or each hour of data be a newer version, right? So there's different ways to think of it.
And is versioning mandatory? Can I switch it off?
Well, it's off by default in the sense that, like, by default, we always write to and read from version 0. So it's really just up to you how you want to use it.
But if you add a new version, you still have to support the older versions, right?
Well, if you write to a new version, what you eventually will be able to do is to be able to read data and have it, merge across versions, which is the way it's meant to be used. Right now, that's not there yet. So right now, you can use versioning as a separate filter. Like let's say that I decide that I version my data by hour, right, or by day. Then I can use that as a really quick way to filter and limit stuff. Right now, that's how it's used.
You allow for some sort of compaction strategies, and you only allow to a certain date to keep versions.
Yeah, I think that's definitely the goal. So the goal eventually is to, like, let's say I only want to keep the most recent 100 versions, and then that gives you a way to, like, deprecate older versions, but that's not done yet. But the more folks say, hey, that's really cool, and we want that, then the faster that'll happen.
So what was your motivation behind versioning? I mean, I'm not aware of.
Oh, I'll tell you, like, the versioning originally came from because I worked for a company that hosted a lot of public data sets. And when your data sets are like sensitive things, such as how much politicians are paid, or things like that, you don't want to just push changes out like a regular database. You really want to have changes and let people look at it, right? So the review process is very important. And the other use case came out of doing geo stuff. Like I might have in public data sets, it's very common to have location column. Like for example, San Francisco has a 311 data set, like all the 311 incidents and 911 incidents that happen. And so you get a latitude and longitude. But you might want to annotate that, right? Like you might want to find out what voting districts these things belong to, or what zip code. And so there's several ways to do that, but none of them are that pretty. So you can think of computed columns as one way to do it. And sometimes these things change, right? Like say zip code boundaries or political district boundaries change. So versioning, again, becomes very important. So there's a couple, and the way that we were doing it before something like this was that we would use a regular RDB mess, and you would have a table, right? And versioning meant you had to copy the entire table and write things over. And you can see what happens when you start getting millions of records, right? That doesn't really scale, right? So those are some of the original use cases behind it. You can think of versioning as enabling streaming too. So let's say I have different inputs, and I just arbitrarily segment them into different versions. They result in different versions in PhiloDB, and I can stream them out and query them separately. This says Spark SQL, but I think I really meant for that to be Spark streaming. Or I'm not quite sure I remember what I was thinking. So a little bit about the how. Some of you asked about how do we store data. So there's multiple ways to accelerate queries in PhiloDB. The first one that I talked about was columnar projection, which is when I do analytical queries, I'm only going to read out the columns that I need. So that saves me I/O. The second way is filtering by partition key. Again, let's say that I only want to read data on a few entities of my IoT or something like that, right? A third way is by doing sort key filtering. Let's say that timestamp is my sort key. So again, I might not be interested in data for all time. In fact, most likely I'm only interested in the most recent time period. So why read all your data, right? And finally, versioning is the last one. And what I would say is you could kind of do this with Parquet in one of these dimensions. Like you can organize Parquet files into a tree structure, but you can't do it in multiple dimensions easily, right? And we're going to go even farther with this concept a little bit later by doing Vertica-style projections, where you have multiple ways of sorting data in the database, and to make that very easy. Columnar format, so again, how does Columnar solve the I/O problem? Let's say that one of the questions is, how much data can I query interactively? And with Columnar, it's a lot more than you think, because maybe I have 100 megs of data, and you think, that's kind of too big to query interactively, meaning at web speeds. But if I only query a few of the columns, maybe that comes down to 10 megabytes. And because I store things in a columnar way, that gets stored in a compressed manner. Like strings, we can use things like dictionary compression, and with integers, we can store them more compactly. So you end up being able to interactively query data that's 3 megabytes. That's a lot more doable, right? You guys will get the slides later, but I have an interesting project called Cassandra GDOUT, where I took the GDOUT public data set. How many folks have heard of GDOUT? GDOUT is the global database of events, language, and tone. Basically, it stores every single political event that has ever happened since 1977 and rates it on a scale from 0 to 10, and how much it's mentioned in media, this kind of thing. So it's a really, really interesting data set. I took this data and I wrote it in several different layouts. One was a regular Cassandra, what I call a narrow table. A narrow table means that you have a primary key that is also the partition key and no clustering key. I also did a wide table layout where I kind of hashed and divided the data set into n sets and rolled this out. And what I found, which was pretty astonishing, and one of the motivations behind doing this project, was that a columnar layout actually gave you huge boosts in both read and write speeds, which is very, very interesting. Some of you asked about the schema. So this is the way that we store the binary data blobs in PhiloDB. We have a partition inversion, which is the partition key. And what happens is that this is the clustering key. What we do is we group the data by the column name first. So like all of the first names are stored together, all the last names are stored together, and so forth. That alone allows you to read out just the data that you want and minimize I/O. Right. The second thing is that we have what is called a segment. So basically, if you think of your data that is sorted from A through Z or whatever it is, we then subdivide it into segments, and so the data, and that's how we keep data sorted as it is being ingested. That they keep going into the same segment. And finally, they're written in successive chunks using successive flushes using chunks. So if you're curious, that's how we store data in Cassandra.
Segment ID is type globe. You do sorting on it?
Yeah, so so we encode data in a way that we can still sort it using a blob.
And trying to visualize how it fits into Cassandra. So suppose we don't use version, so it's 0. And
Yeah.
then partition, what would usually?
Well, the partition is your partition key. So, I mean, let's say for a time series, it's your device ID, for example, would be your partition. And so segment ID would be subdividing a timestamp. So let's say that a segment is, in my case, let's say it's 1 minute, right? So this would be, plus 10 minutes, plus 11 minutes, plus 12 minutes, of successive chunks of data.
So how many, like each row in Cassandra would be device ID and 1 second chunk of data?
Right, when you say row, right, each physical row in Cassandra would be a device ID, not the logical Cassandra row, which in SQL, which is something else.
So would a timestamp be a good candidate for like a segment ID?
Yeah, the timestamp would be a perfect candidate for a segment ID. Yeah.
So basically, you create a table for every column.
No, actually, so there's a column name here. So we create a Cassandra table for every logical table that you have. Yeah. Or at least one of these tables. The GDOUT is, this is how we actually name it. It's the name of the table and we append something else. Yeah.
So in the primary key, you combine the partition and versioning together. Is that
Yes.
the reason? I mean, what does that mean?
Well, it's so that you can pick out different versions, right?
So those two go together?
Yeah, they go together. So this is a composite,
I see. Okay, got it.
a composite partition key in Cassandra. Yeah. Yeah.
So the lookup becomes easier.
Oh yeah. So you can filter by version very easily. Yeah.
How do you know which versions are available when you query the data?
Right now, you would have to iterate over all the keys. So right now we don't store that, but we might in the future.
Okay.
Yeah.
So this kind of table per each column in PhiloDB.
Yeah. So did I trip something? Oh, okay, cool. No, so the table is for logical table. All the columns in your table are stored by the column name. Yeah.
Can you just
Oh, the chunk ID is for differentiating between successive flushes. So basically, the data is kept in a mem table, and then it gets flushed out in successive iterations, right? So let's say in the first flush, your chunk ID would be 0. And the second one would be 1, and so forth. So it's so that it's so that the write path is mostly append only, and every time you flush, we flush new chunks of data. That's all that really means. And it's a way of enabling us to keep data sorted, but still keep ingesting new data. No. This is great. This is a lot of questions about the Cassandra layout. I just have one slide on basically we store data in a way that minimizes caching overhead. And that's one future way of getting very high performance, which is that the data format in Cassandra is stored in a way that such that we have to do very minimal work. When you load it into memory, it's the same format when we scan through data. This is not the same as well. By comparison, when you read normal data from Cassandra, it's stored in S table format. Then when it's read over the wire through TCP/IP, that's a different format. Then when it's stored in Cassandra, it's stored in Cassandra RDD objects, which is kind of another translation. So every step of the way, there's kind of like a separate translation, right, into something else. So whereas PhiloDB is designed from the bottom up, the storage format and what's scanned in memory is the same. So it kind of minimizes that overhead. This is really hard to see, but basically the architecture, like there's a columnstore API, and when new data comes in, it comes in through a coordinator, and it's kept in a mem table. Then it is done through a reprojector, which basically reformats it into columnar format in different sort orders and writes it into column store. The column store API is generic, so we can implement new backends for it. And currently there is a Cassandra and an in-memory backend. But if you feel like, oh, I really like Redis or something like that, and there's always a few folks that like Redis or whatever your favorite store is, hey, feel free to submit a PR and add your favorite column store. I'll go over this a little bit later. Basically, each data set is actually stored using 2 regular Cassandra tables because in addition to the binary blobs, there's another table that allows us to index stuff or it basically keeps track of sort order and overwriting rows and things like that. So just a few quick notes about how, like, future plans. One is that the Philo repo is actually the binary format itself. It's designed for very fast, like minimal or no deserialization, and it's designed for on and off heap reading of binary vectors. It's very, very fast. It's basically the ceiling of this library. I have benchmarked it, for reading integers at, a billionth of integers a second. So this is pretty much the fastest you can do on a JVM without resorting to GPU and things like that, or SIMD, which.
Going back to your previous slide, you mentioned that it's good for random or linear access.
Yes, that's right.
Linear, I understand, but how do you get fast random?
Well, it's basically just a design trade-off. Like most libraries, like most formats like Parquet, is optimized for space. So it will do all the tricks, like all the compression necessary to get in as few space as possible. I guess I have a different philosophy. I mean, space is important, but I believe the RAM is getting cheap. And I optimize for CPU speed, right? So basically, instead of using every compression thing under the sun, for example, like run length encoding is very common, right? So you might use run length encoding to minimize the space that something uses. But instead of run length encoding, what we do is that the philosophy of Philo is to split up data into smaller chunks. And so each chunk you can optimize separately. And to say, instead of run length encoding, I'm going to store stuff using a few bits, but it's consistent. So that way I can do random access. And so I can do like binary search and that kind of thing, without having to deserialize everything. So it's just a different trade-off. Different design trade-off. And the other advantage of this is that, again, I can use techniques like memory mapping files from disk to memory, and I keep it off heap, and I can do like almost no translation, which again, like every step of translation, I think that's one reason why Parquet is fast, but it could be much, much faster. And one of the reasons is because it has to do spend a lot of CPU to deserialize things and that kind of stuff. So yeah, this can be very, very fast. By the way, if you like Scala, by the way, how many folks use Scala here? Just curious. Awesome. This is not a standard for loop in Scala. For I, 0 until num values optimized. This is a macro library called Scalaxy, Scala XY, that basically allows you to use for loops, but give you give you while loop performance, basically as fast as you can do on a JVM, but in a nice looking way. So Spark has a project called Tungsten, which is coming, which will speed a lot of things up by processing data off heap. And one thing that we're planning to explore is to use an actual columnar query engine in Spark. Today, Spark goes row by row, but we're going to look into like columnar primitives, which will get you even faster performance. Because one of the things that slow us down is that we have to translate things into rows today. You got Spark to process it.
So is FiloDB compatible with Tungsten now?
Well, I mean, Tungsten is something that will just benefit all apps. So yeah, it will be compatible. But basically, anybody that runs in Spark is compatible with Tungsten, if you know what I mean. Like, you just have to support the latest Spark versions. But do we take advantage a lot of it? We probably don't take advantage enough of it right now. So we'll be looking more into that. Another thing is that we'll be looking into caching and Tachyon. How many folks know about Tachyon? So for those that don't know, Tachyon is a project to it's basically a caching mechanism that it's associated with Spark because it's developed by the guys at UC Berkeley also. The idea is it keeps your data off heap, but it also keeps it, it allows you to share multiple JVMs. It allows you to share the data across multiple processes. So it's like an off-heap, off-process cache. And some people use it to cache files, like Parquet files. What we want to look into is Tachyon has a feature for tables to store individual columns. So we want to take advantage of that to keep hot columns and share them in memory. The reason why we want to do that is because right now, if I cache data in the Spark workers, what happens when the Spark application dies? Does anybody know? And you lose all your data in your workers, right? So it's not very XA right now. Tachyon is more XA in the sense that even if the Spark workers or your application dies, the Tachyon nodes still exists, so you won't lose your data. And finally, like on the roadmap, to support different ingestion APIs, support more data types, support projections. How many folks know about Vertica, right? If you've used Vertica, then you know that it has different kind of projections, and that's one way of speeding up queries, right? And using GPU and SIMD instructions, this sort of thing. Yep. Yeah. Right now, we support kind of the different integer types, doubles, strings. Let me see. We support most of the basic Spark data frame types.
Do you support like map structures?
Yeah. So today we don't support those yet, but we'll look into adding that as, for not so much like just for having nested data structures and that kind of thing that you typically find. So yeah, would be very interested in your use cases and data models. So that would help us a lot. And just want to end with a quote that my favorite African proverb: if you want to go fast, go alone, and if you want to go far, go together. So this is definitely an effort that we wanted to go very far, and we'd like the community involvement which is why we're kind of opening up at an earlier stage to get community feedback. So we'll definitely like comments and suggestions and use cases, and that would help guide our priorities and things like that. Yep. Thank you very much. Oh, I have a quick demo. I'm going to try to get this going, but demos never quite work, so we'll see. Can you guys see that okay? So this is the Spark Notebook. How many folks have used Spark Notebook? Yeah, so this is, if you don't know about Spark Notebook, so this might just not cooperate because of what the Mac likes to do. Yeah. Spark Notebook is a really neat project that, let me do something really quick. Basically, Spark Notebook allows you to get a notebook-like environment running on Spark. You can keep, especially you can keep your previous results. You can run new results and graph stuff. It's really neat, right? Okay, and okay, so and you can open up notebooks. Okay, this will. All right. Well, anyway, I'll just open up for questions while I'm not really sure if this will work or not, like I said. So, and if we get it working, I'll show you some stuff. Okay. Anyway, something is wrong, but I'm not going to debug it now. Expected host name. Is there Wi-Fi here, by the way? Wait, what's, okay, so nerd.
Nerd sat play or nerds at play, depending on how you look.
Sorry, I can't really read that. Can someone spell it? Yep.
N-E-R-D-S-E-A-T play.
Okay.
P-L-A-Y.
Okay, thank you. All right. Sometimes, Spark, does funny things to the network, right? Anyone found that? Sometimes it doesn't work unless you have networking. But feel free to ask questions while try to get this up and running.
So,
No kernel.
who is behind the project? Is it your personal toy? Is it your company project?
Okay. So who's behind the project? So, this is supported by a company, TupleJump. It was a personal toy for a while. But no, there's actually people around it. Oh, yeah. So I think this is actually running. And so what we do is that, can folks see, or should I make it bigger? Let me make it a little bit bigger. So basically, we start up with a Spark, a SQL context. And here we read in a data set. So this is very similar to reading any other data set into Spark data frames. Basically, I'm doing a SQL context.read.format. And I give it an option, and I do a load. That's fairly standard of use data frames.
What is the size of the data set?
The GDAL data set I have is 4 million rows times 60 columns. It's about, 1-2 gigs. Oops. And whenever you run SQL commands, you have to register a temp table. So after this, I can do, I can basically run so this is the data frame DSL. I can do a select count through Spark DSL. And this is pretty much, instantaneous. This takes like half a second or so. I won't run the Cassandra one for you, but if you were to do the same thing on Cassandra, it would take about say 200 seconds.
What it counts?
Sorry?
What does it count?
Oh no, this is very dumb. This is just counting the number of rows in that are not null in this particular column, which is just month year, which happens to be the month in a year. So that doesn't do anything. But let's do something a little more interesting, right? So let's say that I want to find out the top political events in this data set. And that's by the actor one name, and so I'm doing a select, that and account, and I'm grouping by, and doing an order by count, right? So this is a bit more interesting. So I'm going to do that. It returns the top results. I'm not sure why the top one is blank, but I guess there's a lot of events that don't have a description. But the U.S. and Russia are some of the top events that show up. Let's say that I want, so the table is nice, but let's say I want to graph this, right? So I'm just doing the same query, but instead of just displaying the result, I'm going to actually do a bunch of transformations in Scala to get into a format that the notebook can understand. And now if the Mac will cooperate with me, yay. So now I can actually get a nice chart, right? So this is very fast and interactive. And so I can even do machine learning. Basically, I can, this is using the MLlib statistics library. I don't know how many of you know, but MLlib actually has a statistics library. So let's say that I want to do a correlation between two columns. One is the number of mentions, and the second one is the number of articles. And they both have similar meanings. I forgot what the exact meaning is. But basically, this is something that you would expect to have a very high correlation. And basically, I'm going to run this. What this is doing is, first, I'm going to do the, I'm going to select one column out of the data frame. Then I'm going to map it into an RDD of double, because the statistics library works on RDDs and not data frames. I suspect that they're going to rectify this soon. Then I'm going to run a Pearson correlation, and this has already come out. There's 98%, as we suspected. It's fairly high, but this just shows the flexibility of something like PhiloDB when you connect to Spark, that I can run the machine learning library and do all kinds of interesting things, and this comes right out of the box. So, cool. So yeah, thanks for coming, and. By the way, I'll just mention again, we're open to helping folks with development projects and big data, and be very happy to take questions about PhiloDB and other things.
What is the disk usage overhead for PhiloDB compared to standard Cassandra?
What is the usage overhead of PhiloDB compared to standard Cassandra? Haven't really profiled it. I think on the read side, compared to standard Cassandra and Spark, it's fairly similar. Memory might be a little higher, but definitely the CPU and resource is a lot lower because it runs a lot faster. On the ingestion, it's going to use up more memory than Cassandra, just because in order to convert to columnar chunks, we need more memory to have. Basically, the idea is the more memory you can use in the mem table, the more efficient the writing will be, because it will write in bigger chunks. So it's kind of a trade-off. What kind of compression libraries do we support? Was that a question?
No, what compression libraries do you support?
OK. So PhiloDB itself doesn't do compression on the data. However, Cassandra itself has a lot of compression options. So the standard one is LZ4, and it can also do Snappy and I think a few other ones. So what I've seen on the GDAL data set is using the built-in LZ4 compression. It will compress, even though the columnar chunks are already very efficient compared to the native Cassandra storage format, the LZ4 gives it an additional it compresses the data down to a third of what it would be, is what I see. So yeah, so it's definitely, I think it's definitely worth it. Yeah.
So a couple things. So one thing I want to understand with the versioning.
Yes.
Is it data versioning or schema versioning?
It's both. So the data is versioned because the data is actually written to different physical versions. But the schema is versioned as well in the sense that, let's say that I have columns A, B, C, D. I can always add new columns to my current version, but I can't change, for example, like if I want to change the type of a column, which you typically don't do in Cassandra or NoSQL anyway. But let's say for some reason I wanted to change the version of column A from int to a string or something. So you can't do that on the current version, but I can do that in the next version. And then that allows me to separate out the data. And I can do my ETL from version 1 to version 2. So it's both. And deleting a version is actually just marking a version, deleting a column is the same as marking a column as deleted effective version n. So if I was to query version n-1, then I would still see the column. And if I query version n, then that column disappears. So yeah, so it's both.
And then another question, what would you need to do to get this running under AWS?
Well, pretty much I would run set up Cassandra in AWS and Spark and collocate them. There are different ways to do that. One of the neatest new ways of doing it that I've seen is that Mesos has a DCOS that you might have heard about. It's called the Data Center Operating System. And with that, you can pretty much, you give it your AWS credentials, and you can do a DCOS package install Spark and Cassandra. Then it will set things up for you. But yeah, that's.
What about the connecting to Mesos? It's like Kafka.
So that, that's not specific to PhiloDB, but there's different ways of doing that too. Like you can connect Spark streaming to Kafka, for example, and so yeah.
I'm not too familiar with Akka. Could you explain to me a little bit how that fits into the framework? What does that?
Sure. A little bit about Akka. I don't know, do you want to say a few words about Akka? So basically, Akka is an actor framework. I don't know if you've heard of Erlang, right? But the telecoms invented this new language back in the 70s. What Akka, let's see, what's the best way to describe actors? It's basically like people talking, right? The idea behind actors is instead of sharing, let's say you have one box with multiple threads, you share mutable state. That's kind of like traditional Java application architecture. Actors are very different. Actors is basically every entity is like a separate person. And the only way you talk to each other is by sending messages. You don't share state. And because and everything is, so one thing is you share messages, and another thing is that people watch out for each other. So if there's a fault in one actor, then somebody else supervises it and can restart it and can be responsible for it. So that pattern allows you to easily distribute applications. It's just like having a distributed organization. You have people talking to each other, but instead of seeing each other in person, I can still exchange messages through email, right? Or through Slack or whatever it is. So actor-based programming gives you a really easy way to distribute applications. In the case of streaming, I would say actors are a great way to do real-time event processing with very low latency because you can easily exchange like millions of messages a second. And you can operate one message at a time. So that's where it fits in. Like one way you might use it is I can use it to read data and feed it to Kafka. And I've used it in the past to process messages out of Kafka and as like independent processes and forward to other things. So, all right. Well, thanks very much. I'll be available afterwards for questions, and stuff. Yep.